Greetings, everyone, and welcome to the Complexity Lounge, a meetup where we gather to talk about all things related to complexity and complex adaptive systems. I'm Jocko Stelberg, and I co-host the lounge with Barbara Frontera and Tiani Jones. Today, we welcome back Alicia Juarrero to help us kick off our 5th year of the Complexity Lounge. Alicia is the founder and president of VectorAnalytica with a doctorate in philosophy from the University of Miami, where she is also currently a research associate. She is the author of the books Dynamics in Action, republished in 2008, and Context Changes Everything, 2023, both available at MIT Press and fine bookstores everywhere. Today, Alicia will be discussing her latest thoughts on a number of topics, including, but not limited to, Buckminster Fuller's concept of tensegrity, Tim Allen's notion of gain as applied to economics, and the notions of meaning and value in reference to complex systems. Whew. So, Alicia, welcome back to the lounge.
Thank you so much, Jocko and Barbara and Tiani. I always say coming back to the Complexity Lounge feels like coming home. You guys were early adopters of these ideas. So I thank you very much, and I look forward to these next few hours. As you might see from the title, I kind of chickened out on the idea of norms, and I added something else, and I'll explain why a bit later. But what I hope is that many of those in the audience, and as I was looking over the names, I hope I'm right, that you're somewhat familiar with my ideas about constraints. You're familiar about my ideas about enabling constraints and constitutive constraints and constraint regimes, and how those self-organize and are enabling constraints from the bottom up, and they are constitutive and governing constraints from the top down, from the whole to the parts. And I thought when I was speaking to Barbara about this one, I thought, let's do something a bit different and novel. I mean, enough with the constraints. To me, it's a bit old hat. So then the question is, how else does the notion of constraint apply to what else, why, and so on? And I'm a very disorganized reader. I kind of read whatever, and I'm a very disorganized filer. And so I all of a sudden came across a number of papers that, as you will see, are oldish. They go back to the 80s and the 90s. And as I was rereading some of these, I'm thinking to myself, gee, am I glad I didn't remember about these papers and these books, because it would have made Context Changes Everything 4 times longer, or I wouldn't have written it at all, because I always have figured, oh, these folks figured it out early on as well. And I think they're connected, and so I'm going to divide this, I hope, into 3 parts. Gallia est omnia. This presentation is omnia divisa en partes tres. I'm going to do tensegrity, and then almost like Act 2, completely seemingly disconnected, I'm going to talk a bit about the notion of gain, not in electricity, but in economics and biology. And then in honor of Stan Salthe, who passed away in his mid-90s only a couple of months ago, and he was a dear friend, and he was always very supportive of anything, any crazy thing I wanted to say. I'd like to look at some ideas about infodynamics that he and a few others in the 80s and 90s started talking about, and somehow, I don't know why, but that seems to have fallen by the wayside. People don't, or maybe it's me. And the curious thing is that Salthe, in that work on infodynamics, talks about and references Tainter and Tim Allen, not Peter Allen, Tim Allen's notions of gain, and also Dan Brooks's notion of entropy, and information is entropy. And so I suddenly realized, well, I'm not the only one who's connecting these ideas. And so what I then want to do towards the end is tie it all together, but please humor me, and let me present the 3 separate ideas. I will get a bit unclearer more muddled as I get to infodynamics, because in a sense, what I'd like to do in this presentation is have you join me in thinking these things through. I don't claim that I've thought the whole thing through entirely yet, but it seems to me there's some interesting ideas to be gained. And so let's start with tensegrity. If you've ever taken a look at this, at the notion of tensegrity, and you go online, there's zillions of little videos and GIFs and all sorts of things on tensegrity on YouTube. And so I encourage you to do that. There's they're really very nice work. And if you look at this image, you see that it is a three-dimensional structure. It is a three-dimensional structure composed of two-dimensional elements. There are what are called compressive or compression elements in green. These are usually struts or rods or whatever you want to call them. But if you look very carefully at this little video as it twirls, the green rods do not touch each other. They are completely independent of each other. In a sense, when I look at this, I think to myself, Newton also thought atoms were independent of one another. And thermodynamics thinks of particles as independent and isolated from another. But then look at the elements in red. These are called tensors, or they're tensile elements. Oftentimes they are flexible connections like rubber bands, and they link the previously independent green structure elements into a continuous network. And what's cool about this is that the manner in which the flexible connections are arranged, that word arrangement will show up again in the form of order, organization, and so on as we go through this. The way these flexible connections are arranged in a continuous network allows for mechanical stresses to be evenly distributed throughout the 3D structure, such that the structural form is preserved. Now, this was a term that was coined by Buckminster Fuller in a 1961 issue, and in, what is it, Synergetics, he talks about it a lot. And I guess I didn't realize that until recently that Fuller claimed that tensegrity was indeed the fundamental principle of the universe. So once again, we've got two different elements in a 3D tensegrity structure. The components that are in compression, I've never understood exactly. I guess what it means is that if you press any of those rods into the center at some point, it will snap. They will snap. They're in compression. And the red tensile elements are in tension. And so he coined the word tensegrity to see how they're connected to one another. One, the components, the green rods, might be rigid, but they are not rigidly connected to each other. It's the tensile elements that are flexible and flexibly connected that are critical in establishing and maintaining the characteristics of the 3D structure. Let me it's amazing how flexible and how resilient tensegrity structures can be. However, they are not infinitely adaptable. I was trying to download a video that showed that some of these tensegrity structures can bend and deform while maintaining a certain degree of integrity at a certain angle, but they may not be able to do it in other angles. But the main points that I want to point out here regarding tensegrity structures, it's the tensile elements. It is the connectors. It is the red links that self-equilibrate a tensegrity structure. And they do so, as I suggested, by distributing internal stresses across the structure, which allows the whole thing to adapt without losing overall cohesion or integrity. In other words, the structure as a whole maintains its identity. So again, they are exceptionally strong and resilient because there are no shear stresses within the system. They are self-equilibrating because they have distributed connectivity, which allows them to adapt to various varying loads without losing structural integrity. Interestingly enough, there are again a number of videos online that show how this design pattern supports scalability and modularity. So again, what I was interested in as I was looking at this is not the fact that it's a rigid structure that twirls prettily, but rather that the principle of tensegrity is a way of producing a coherent structure. And the word coherent, as you know, is one I'm very interested in because that's what I sort of based a lot of context changes everything on. It allows these dynamic structures to adapt and expand in size and complexity, right? So obviously you can see where I'm going with this. Are constraints somewhat analogous to tensile elements? And my answer is yes, but even better, they support not only adaptability, but also evolvability. So I am looking at this with constraints in the back of my mind, but looking at it from a bit of a different angle. Now, I included in the deck, and I will share the deck with Jocko, and so you guys have access to it, that's fine. I don't know whether you can see this image well, but what I tried to do was take a look at tensegrity, and then what I'm calling consegrity. So it's the idea of constraints as the tensile elements in a system, and how the distribution and so on enables the emergence of a continuous network that, of course, in my view, includes emergent properties, and that it also allows for the structure as a whole to maintain itself as a dynamic whole, thereby allowing potential for resilience and evolvability. That's where I'm going, but I don't want to spend too much time on this. There's some notion of presetting that Fuller talks about, and that is, well, you've got to decide, are these red tensile elements that link the independent components together, depending on which are what length and where they are connected, you will get a structure that is, in the case of Buckminster Fuller's rigid system, more or less stiff, more or less stable. But I think that you can perhaps, and here, this is something it's to be done. I keep coming back sometimes to context-independent constraints and thinking, well, are there existing gradients and polarities and charges and handedness that we live in this light zone, light cone. We live in this history. We live in this society. These are, for our purposes, for purposes of ourselves, preset. So could that be an analog to the pre-stressed tensile elements, self-equilibration, and so on. But we can come back to this if we have time, but we could spend 2 hours on just this slide. And as I said, this is a work in progress. I'm not sure that I've got this all correct yet. So that was Act 1. So think about tensegrity, tensegrity structures, and a possible analog with constraints operating as the tensile elements that generate a multidimensional structure and are able to maintain themselves thanks to the interlocking interdependencies of those tensile elements. And now I want to turn here again. This might be 2009, a paper by Tim Allen and Tainter, and this one also happens to have Peter Allen as well, who tried to apply the notion of gain to ecology. And clearly, this was a situation where Tainter had written this book in 1988 about how complex societies collapse. And Trent brought it to my attention a few weeks ago, and I'd completely forgotten about this book, which is very good. And the answer that he gives is, well, societies become more complex and become more organized and more coordinated in order to solve increasingly difficult problems. And the benefits of complexity at first increase, and this is a stage of high gain, and they eventually decline. They show diminishing marginal returns, which is an attempt to apply the notion of economic return on investments, especially economic return on energy investments, to ecosystems. Tim Allen is a biologist, a hierarchy theorist, as is Peter Allen. He's a complexity theorist. Tainter really is a historian and an archaeologist. Very interesting, interdisciplinary effort here. Okay, so what are we talking about here? For those of you who know gain from electrical engineering, please kind of put it in the back of your mind. I can handle this nicely because I don't know that story that well. But think of conditions of high gain as conditions where you have a high return on investment, because in a sense, there's minimum to no investment cost. So a high gain system, as Tainter and Allen define it, are systems that use readily available resources. So I think of not even hunter-gatherers, but just plain old gatherers of berries back in prehistoric times, or they gather berries that they happen to run across, or they pick fruit that happens to be low-hanging and is on the path that they happened to be walking on. Or what is it, that hand fishing, you're near the stream and stick your hand in and pull out the trout or whatever it is, right? Or drinking water from a nearby stream, or if there's plenty of rainfall, you just cup your hands out, drink some water. Burning wood for heat in an area with ample supply of easily culled twigs and small branches. And in a sense, perhaps we could even say early Oklahoma gushers. I don't know. In other words, the resources are there for the taking. They're ready-made. Something other than the system at hand concentrated the resources. It's flora, evolution that produced the berries and the fruit. It's geological history that produced the drinking water from the nearby stream, and so on. So the resource is ready for the taking without much need for refining what is gathered or organizing to secure it. So they present the notion of high gain as, you don't have to sharpen the stone to kill the small prey. That's the next step. But right now, it's just, you just stick out your hand and you pick up the mouse or whatever. Obviously, the point being here that high gain conditions do not last. at sooner or later, low-hanging fruit becomes depleted. So the point that Tainter and Allen make is that high-gain systems must become low-gain systems. Now, low-gain systems, you turn to low-gain, oh no, let me put it differently. Low-gain conditions are those where the quality of the resource is not as good, or the resource is becoming depleted. So there's either less flow in the river, or the river got muddied a bit. So it's not nice, clear spring water. Or the harvest amount is diminished because of environmental issues. Or the gradient that allows it to flow easily is shallower. So the fruit is higher up on the tree. It's not as easily. All right. So more of it must be gathered. You need more workers to get the same output or the same result. What is gathered has to be refined. You've got to either put that muddied water through a filter, meaning you need different equipment. Somebody's got to figure out that equipment. I'm thinking of the twigs with the chimps trying to get at the termites, or the whole notion of tool making up to fancy oil refineries. Or, and here's the main point that Allen and especially Tainter is making, and that is all of a sudden you have to become socially organized to acquire that same number of calories, say. So a transition from high gain to lower gain is a transition to complexity and organization. Now, let me explain this in some, here's an example of ant colonies. And the ordinate on the left is the benefits of complexity, and the abscissa, do I have this right? The other way around, evolutionary time. What happened was that, as we think, biology tells us that you started out with food gathering ants. So ants just ate food that they happened to run across, flowers, for example, right? And what happened was that when under conditions of high gain, folks, if I do this, can you see my cursor? Well, I don't know.
Yes, we can.
All right. So this is a perfect example of, in the conditions of high gain, you can get a large increase in the population because low-hanging fruit can get you more calories, can get you more reproduction, and so on and so forth. But as the theory goes, sooner or later, that peak, in fact, very quickly, according to, which is the problem I may have with it, starts becoming depleted. And so over time, it stops supporting the same number of individuals that it used to. Now, what happened, according to geologic evidence and archaeological evidence, is that suddenly, when they reached the trough, a group of ants began gathering grasshopper feces, which takes a lot more work to acquire than obviously just picking the flowers that happen to be in your path. So it is a low gain enterprise compared to gathering food directly. But on the other hand, grasshopper feces, according to Tainter's terminology, are like jet fuel for growing food. So they could use the grasshopper feces to grow the food that they used to just pick on the trail earlier, right? So takes more energy. It takes a certain amount of organization. I won't go into details. Tainter and Allen and so on go into long detail about exactly why is it that gathering grasshopper feces to then cultivate the food that you're going to eat requires primitive but definite social organization. But the point I want to make is notice that the low gain system can capture more usable energy than the respective earlier high gain. High gain was easier, but lower gain will ultimately overall get you more, meaning it can thereby support a larger population. And so obviously the point that they were making is you're going to find, and on the next slide will show it, let me finish here for a minute first. You're going to find an evolutionary pattern of resource refinement and varying levels of gain concomitant with increasing complexity and organization. So one thing I want to point out is that, if complexity has a million definitions, well, here's another one. They're using the notion of complexity and organization synonymously, meaning you're going to have more types of elements used differently, interconnected in a way to produce a goal or a purpose or a function or an end. And therefore you end up having these kinds of ants, food gathering ants, becoming a different species from the fungus farmers. Now, obviously, those of you who are familiar with context changes everything, you know what I want to say. What I want to say is constraint regimes are different kinds of dynamics and forms of organization that result in different types, species of ants. So constraint regimes are different low gain patterns, I would like to say. But the point being, low gain can, right. So now the earlier slide, I wish I could show both at once. The earlier slide is this and this, correct? So you had the food gathering ants, and then all of a sudden you've got farming ants. But here's the initial effort of cultivating grasshopper feces to grow the food directly. But what happens in the end is, of course, once they're able to harvest the food they grew with the grasshopper feces, then it'll grow here as well. And the pattern repeats. Apparently, at some point, as I said, grasshopper feces are jet fuel for fungus farming. But it's hard to do. It's hard to find the grasshopper. It's hard to find the feces of the grasshopper. But all of a sudden, another group of ants discovered that they can gather leaves, which are initially much less. Leaves are not jet fuel for growing food the way grasshopper feces are, but leaves are everywhere. So in the end, a mature colony of leaf-growing ants will end up emerging as a result of this high gain, low gain dynamic. So increasing complexification is also an increase in forms, right? Or species, call it that. Increasing complexification is not increase in numbers. It's the increase of types of entities, from food gathering ants to feces growing ants to leaf cutter ants. And so it's an increase in the variety of elements that a constraint regime, in my language, has to coordinate, handle, control, manage, right? If you prefer that terminology. So Tainter's take on the implications of gain is that it ultimately leads to collapse of complex societies. And you saw that in the first slide where it goes up and quickly deteriorates. More likely, however, the problem is that the investment in greater complexity itself becomes a vicious cycle that satisfies the second law. So it's not just a matter of when you look at the images of LA, the horrible images of LA, and when you see that the water pressure in LA was impossible to sustain at the level needed to save 12,000 built structures using hydrants alone. And simultaneously. So you get a precipitous catastrophic collapse of a complex city. That would be an example of Tainter's original idea. But as I said, he's a historian and archaeologist, whereas Alan and Salthe are biologists. And it doesn't show a stage of maturity, if you will. So where am I here? Okay, so now Tim Allen, being a biologist and ecologist and a hierarchy theorist, his earliest book I quote a lot. It's called Hierarchy, with Thomas Starr, and they argue, well, but there are no regular catastrophes in nature. Oh, there are catastrophes aplenty, and the meteor hits, and all the previous phylogenetic lineages get wiped out. But there are no regular catastrophes in nature. Nature tends to quickly readjust, either by onboarding fuel creation. So the prokaryotes, which were once unicellular bacteria, engulfed the mitochondria, and so they were able to produce their own ATP, their own energy. It didn't rely on external energy to produce the low-hanging fruit. So the next question is, how does this work? And I will not go over the prairie grass ecosystem and the chaparral ecosystem, because I do mention those in Context Changes Everything. Basically, the story of the prairie grass ecosystem is that the prairie grass ecosystem of the high plains ended up incorporating horses into the very dynamics of the ecosystem. And so rather than fall prey to the appearance of this predator, the horse, they actually incorporated it into the constraint regime of the prairie grass ecosystem. And that's also true of the chaparral. And it's funny, I was preparing this and I'm going, gee, I haven't seen images of whether the verges on the side of expressways in LA were spared, because decades ago, as I recall, in Los Angeles, in most of California, succulents were planted on the verges on the side of the freeways because succulents have internal water, and so they were able to protect the freeways from forest fires or from wildfires that way. But think of the notion of high gain and low gain as to whether the fuel is readily available, and obviously it was in the case of the wildfire. That's the flip side of the coin of the problem, right? So as a result, what I decided to start looking at is the notion of information as it is embodied in biosocial systems. See, the notion of information is not included when Boltzmann talks about his understanding of physical entropy and thermodynamics in the second law. But once you start talking about biological systems, then the notion of the capacity of biological system to have information, and obviously, most obviously in genetic information, and then socially through symbolic information, symbolic coding, genetic coding, symbolic coding. I think there's a transition from physical thermodynamics to biosocial, excuse me, infodynamics that is interesting to take a look at. And so when I learned a couple of months ago that Stan had passed away, I thought, let me take a look. And the more I read about his stuff, oh, this is misspelled. I'm sorry, it's Salthe. The second entry is correct. I strongly urge you to take a look at his work because his first book, Evolving Hierarchical Structures, is just wonderful. And for those of you who think, oh God, no hierarchy, that's what we don't want. No, take a look at these folks' notion of hierarchy. It's the biologists' notion of hierarchy, and then you really understand what they're talking about. And the interesting thing about the paper called Infodynamics, a Developmental Framework, which I'll focus on because it's more recent than what is Infodynamics. I think this one's 2001, but I can't find a copy of the full paper of this one. I only find the abstract. It's a very, and this one has the full paper, so it's well worth taking a look at. And interestingly enough, Salthe cites Tainter, Collapse of Complex Society I just mentioned, and at the time in the early 2000s, Brooks and Wiley, it remains a classic of how you can think of evolution as the utilization of energy and the dissipation of energy and the deterioration of the quality of energy, as well as Bob Ulanowitz's Ecology, which also I'll mention a term that he used in this regard a lot, throughput. So I strongly urge you to look at this. For example, this is from Salthe's Infodynamics. He talks about the development of individual organisms. He's not talking about evolution of species. He's talking about the development of an organism from an immature condition to mature to senescent condition. And he talks about it he says, well, it can be looked at metabolically, just as the use of energy. And so in this regard, especially the bottom curve here, it's reminiscent of the first one I showed you by Allen and Tainter, where it was just up and down from high gain and then quickly collapsing down. I'll come back to this period in a minute because you don't have that broad a maturity stage in Allen and Tainter. And Allen and Tainter is you've got to continue growing, continue consuming energy until the whole thing collapses. It's more of a traditional thermodynamics notion of the process. But this is sort of the traditional thing. But if you notice, there's another pattern that is possible in organisms, and that is, you get diversification, from a single cell fused egg, sperm and egg fused with growth, with diversification or what's the word I'm looking for? Differentiation, right? And the fact that this is synonymous with the acquiring the storage of developmental information. As the organism grows in development and develops, it is storing information of its trajectory. You know that in the two books, I make a big deal about one thing about dissipative structures is they are path dependent. They store the information of the trajectory that they have undergone in their very biological structure. And that, I think, is true developmentally for individuals as well as for the species as a whole, obviously. So if you think of it as energy, how much energy is growing through the system, but then it starts leveling off. All right. In this example, which is Prigoghine's example, I won't go into it. Prigogine talks a lot about the law of minimum entropy production. Rod Swenson years ago was talking about the law of maximum entropy production. So there's no need to get into the details here. But if you notice, Lotka-Odom maximization, there are cases like predator-prey cycles where the dynamic can maintain itself at a fairly high level of complexity without collapsing into disintegration as Tainter had originally presented. So there are cases of predator-prey cycles. And I would like to think of this period, this sort of steady state leveling. See, in this case, what clearly happens is the resources get depleted. That's the old previous image I showed you. The organization cannot keep up with the need for resources to maintain and improve organization. And so you immediately go on to a downhill slope. So, and by the way, Salthe talks about senescence as characterized by being information overload. The system becomes overly connected, and that means that it becomes functionally underperforming. I think of that cartoon that has all the dots, and you got and social media and the internet and so on is just, you're getting more and more and more and more and more of these dots. You're getting an awful lot of data, but they're not connected. So you get functional underperformance, and so the thing starts disintegrating. But also, under senescent conditions, behavior becomes entrenched. At this stage, behavior lacks flexibility, it lacks variability, and Salthe refers specifically to Ashby's point about requisite variety, where the requisite variety, you can maintain variety.
Spread it.
Oh, yeah, David said I'm spreading it. I'm the course.
Hello?
Excuse me one moment, please. David's iPhone, could you please mute yourself? There we go. I got it. All right.
Okay. Behavior becomes entrenched. It lacks flexibility and variability. Therefore, it fails Ashby's requirement of necessary variety, and it tends to start reinforcing existing propensities. It becomes, my terminology is entrenched. It just sticks to it. And so and it lowers energy throughput, which results in toxicity. So it's a very interesting way of looking at it. But I want to go back and take a look at this period of maturity. See, well, what's going on here that you don't get in the original Tainter collapse of complex societies? And what Salthe describes maturity to be like is a period of metastability. It is not static stability. It is not your grandmother's old-fashioned static stability. It is metastability. It is relatively complex, layered organization that nonetheless has achieved a multidimensional steady state. And what's particularly interesting is that this might be the level of gross energy that it might consume, but in maturity, it maintains itself below the level of energy it could utilize. I don't know if I'm making sense. This is hard to explain. The system could handle this amount of energy, but when it does that, if it did that, it would fall apart. But what happens is that under certain conditions, it might reach a steady state level. Look where I'm going. This is adaptive capacity, right? This is adaptive overhead. This is what it could rely on if it needs to under emergency conditions. It's not going to use it under regular conditions. That's where I'm going, right? So it has a certain robustness, and Ulanowitz and a lot of these biologists define robustness as a measure of system sustainability, which they gauge as the relationship between effective performance in relation to maintaining unutilized reserve capacity. I like this. The notion of effectiveness can be maintained longer if it is arranged in such a way that it is lower than the possible maximum reserve capacity, right? And this is going to mean, hey, I've got room to maneuver because I could get more complex here as long as I stay below my threshold. All right. So let me stop for a minute and talk about what Salthe's definition of information is. And again, if there are zillions of definitions of complexity, there are zillions of definitions of information. And he defines especially biosocial information as any configuration that might have been this different, provided it delays dissipation. And I'll explain that in a minute. Well, I'll explain it now. All right, no, but let me do this first. There are two ways that dissipation can happen. Here, and even more so in the earlier slide that showed high gain, and whoops, all of a sudden it collapses to low gain. That's fast dissipation, but it tends to produce higher grade waste. It doesn't go directly to heat. Here's my image, and there's probably a much better analogy, but this is what I'm thinking. Think of consumer waste. A form of fast dissipation is city dumps full of high-grade material, city dumps full of perfectly non-destroyed TVs, laptops, and so on. But there are, I apologize for doing this. There are ways of dissipating, which Salthe calls delayed dissipation, where the way he phrases it, which I'm not crazy about, and here's the point where I said I was going to get less clear. He calls delayed dissipation cases where new but weaker gradients appear so that in the end, waste is dissipated more completely, but it takes a lot longer. And the example that I have is contrast a city dump with the appearance on the scene of organizations like eBay or Goodwill Industries, or here in town in DC, Community Forklift. And notice this requires a certain amount of organization, because all of these, for example, in the United States, allow you to deduct expenses for tax purposes for donating to these organizations. But in each step of the delayed dissipation, the entity, the element the actual TV set, the actual laptop, gets reused at a lower gradient level. So maybe the person who purchases the laptop on eBay purchases it for parts. Or the person who goes to Community Forklift goes to find a glass. I had to go to Community Forklift. I found a glass knob for my 1928 townhouse. That, sure enough, Community Forklift had had boxes of old glass, not plastic, doorknobs that I was able to use to repair my house. That's an example of delayed dissipation. So in a sense, back to the notion of throughput from Ulanowitz, it cycles the what would have been waste in a fastly dissipating system to a slower dissipating system by being part of eBay or Goodwill. In a sense, you can see now what I'm going to try to do is apply the notion of gain and tensegrity to both of this, to all of this. In a sense, the ants that eat, that gather the grasshopper feces are, when they finally grow the plant with the use of the grasshopper feces, are consuming some of the energy that was stored in the feces. So the farming ants, in a sense, are a new gradient that is able to recycle some of the energy more deeply. And therefore, if you have a series of delayed dissipative structures, in the end, it does end up dissipating the energy into heat, totally unusable energy, more so than the fast dissipation of thermodynamics. So I would like to say that enabling constraints are what generate, if I can go back and look at I want to look at I lost the image of the ants. There we go. See, this is a new form of organization. This is a new form of organization. These are new forms of organization. So what I'd like to say is that constraints enable the generation of novel, multiply realizable configurations, and that the constitutive constraints I talk about in Context Changes Everything preserves form and thereby delays dissipation. See, so I don't think I used the term delayed dissipation when I described constitutive constraints and enabling constraints in Context Changes Everything. I think that after looking at these works by Tainter and by Buckminster Fuller and by Salthe, I think I can explain that the transition from high gain to low gain is a transition to a new form of organization. It is a transition to novel information, and that the reason why it delays entropy production, why it delays dissipation, is because in each case, part of the energy remains stored as biosocial form, biosocial information. I think that works. This is just the difference between physical and informational entropy. Let's see, what time is it? I don't want to spend too. All right, yeah, I better stop. So creation and maintenance of multiply realizable constraint regimes is, for me, the informational equivalent of the steady state physical entropy that you see in that sort of leveled off, steady state, mature condition. All right. Now, finally, this is Salthe's last slide. Look at what happens sometimes. All right. What happens at times is that, all right, here's the beginning. Organization isn't sort of coalesced well. So you're still immature, and you can imagine an immature organism, a toddler, an infant, a toddler. Then as things become more, as disorder becomes more controlled, it becomes hierarchically organized. Informational entropy continues to grow. And what you have is that complexity, the complexity of the individual biological organism embodies its organization. But organization is always, and this is, of course, why I'm interested in this, is always multiply realizable. So the organism is manifesting one form of organization, but if things start getting difficult to maintain because things start getting a bit too complex, then, as I said, this is organizational overhead. This is adaptive overhead. So sometimes a mature system can tap into adaptive overhead. And I'm thinking in an earlier talk in the Complexity Lounge, I'm almost sure I spoke about Will's graceful extensibility. Sort of you tap into adaptive overhead, or you tap into organizational capacity to keep yourself in business and not to collapse down into senescence and death. You can still continue to work nicely. And if you don't know what I'm talking about, this graceful extensibility paper, it's the one particularly where he uses the example of an emergency room at a major metropolitan hospital and how they organize themselves in such a way that if all of a sudden you get a real catastrophe, I can imagine what these ER rooms in LA are looking like. They can tap into the personnel in the pediatrics ward, or they can in the OBGYN ward, or they can tap into the resources of some other division or department in order to keep themselves in business. Now, what cannot happen is if they go beyond H max, what do you have? Then you have non-functional and pathological behavior. Now, given that I live in Washington, D.C. and the inauguration is 3 days away, I wonder, am I still here? Can I still handle this? Can the country still handle this sort of these crises? Or are we starting to worry about going beyond maximum entropy capacity, in which case we're looking at a collapse of the entire society? I don't know, but I worry a lot, because once you start reading this stuff and then you open, you read the newspaper, you're like, oh, what's going on? So maturity in biosocial systems would be a relatively complex, steady state that is below maximum complexity, maximum use of energy, and it's preserved thanks to organization and the fact that it is, notice that your wiggle room of error, your wiggle room of mistake is a lot lower when you're in an immature condition than when you're in a mature condition. You got more wiggle room, you have more adaptive capacity, adaptive overhead as a mature. But then, and none of this, the fact that this does not go all the way down, does not by any means, I knew Salthe was a good friend. He was obviously always concerned. The second law always holds. But look at what happens sometimes. Sometimes the system is able to has the capacity to revisit less developed, less evolved, less complex conditions in order to keep itself in business. Now, what I have in mind here would be things like, which also means that for Salthe, resilience means a lot of behavioral variability. So the adaptive overhead is often stored as the capacity to do things differently. So if you have the capacity to do things differently, look, behavioral variety, then you've got the capacity to survive and continue at a pretty high level of complexity and sophistication. Not that the second law doesn't hold, you're just delaying it, but you're delaying it not, you look at the conditions of the images from all the Palisades fire, from the shore highway to the ocean. You go, my God, it's just dust. There's nothing left here. There's no variety. It's become entropy. It's become noise. It's nothing there. But so Salthe makes a big deal about resilience being the basis of the adaptive overhead and the capacity to develop and later on to evolve. So the highest level of robustness correlates with behavioral variability. Now, that's the highest form of variability when it includes non-functional pathological. But typical ergonomic behavior is fairly high level of energy throughput and complexity and organization, but kept in bounds by organizational constraints. And that, of course, from my perspective, is the role of constitutive constraints operating as regulatory constraints that I describe in Context Changes Everything. So, resilience is, for Salthe, the capacity for behavioral variability. It's defined as the capacity to adapt behavior in response and properties in response to changing conditions. I think that capacity is given by the kind of constraints. So I'm back to the tensegrity example. Are those tensile elements that hold the structure, the consegrity structure together, entrenching, freezing, rigidifying constraints? Well, those aren't going to serve you at all to promote resilience. Whereas generative constraints that are flexible and adaptive enough to be responsive to the local condition, that will support resilience because it gives you the right level of behavioral variability. Not crazy, do anything, but rather, there's a method to your madness. You're doing this for a particular, because of particular organizational constraints. So in summary, at the end of a high gain situation, find yourself a new type of high gain fuel. I'm not sure whether generating your own fuel counts as a new high gain situation. We know, for example, that way back in geologic time, at one point, oxygen became airborne oxygen became generated, and that changed everything. That's the whole Gaia Bruno Latour thing. Or as I said, it engulfs the mitochondria, or to generate your own ATP. Or when we created symbolic information, does that count as a new type of fuel or a new type of constraint? Or if you lower dramatically the cost of constraint, what happens there? Why am I asking that? Is artificial intelligence and ChatGPT, is this a new form of constraint? Is this a new refinement? Is this like going from grasshopper feces to leaves? Or is this going like an entirely qualitatively different process? A new type of enabling constraint. Is the origin of life a new type of enabling constraint or a new configuration of the earlier constraints? Existing enabling constraints arranged differently. Coded genetic information, evolution of symbolic information. Is this a third type of constraint? So what's the moral to be taken from all of these put together? I think that if these ideas are correct, then our task as managers, as thinkers, as leaders, as thinkers, is to think of social organization as a type of dynamical tensegrity structure where qualitatively different context-independent and context-dependent constraints don't just refine existing configurations, but they generate entirely new form of order. So if order is a measure of constraints, enabling constraints make possible a higher level of organization, and the kinds of, and this is what I spent the last chapter of Context Changes Everything doing, is what we need are generative constraints that produce multiply realized, which Salthe calls complexly disorganized, meaning they're complexly disorganized because they're being characterized by behavioral variety that makes them resilient, basically. And they're held together by constitutive constraints, but they're not entrenching constraints. That only produces senescence. They retain sufficient uncertainty and indeterminacy in the form of possible new behaviors that maybe haven't been tried yet, that may counteract entrenchment and allow free evolvability. So this is it for me. That our goal is to arrange constraints that enable and generate order, that preserve mature metastable conditions and do not exhaust adaptive overhead. And I think this is underpinned by the sorts of constraints that are context dependent and that are enabled by a large variety of components and levels of organization. And that's why these folks talk so much about hierarchy theory. So metastability supports resilience, evolvability, while preserving identity, even as they allow some incursion into adaptive overhead to handle emergencies and adapt. That's it. Okay, folks, sorry, let's see, what time is it? My goodness. About an hour and 10 minutes.
Need the sound
Well,
of applause.
That was, yeah, Zoom needs to work on their reaction stuff. Yeah. We need audio. Well, Alicia, that was great. You brought together a bunch of concepts that, you referenced in the past or that you developed, and I'm really excited. The link to the Tainter paper is in the meetup announcement. We will also make sure that we put links to all of the research that Alicia referenced into the description of the YouTube video that will be posted within the week. So don't despair if you missed a reference. We got you. So now I was trying to pay attention to the chat, but I didn't see any questions in there. I mostly saw comments. If you have a question, it would be great if you could raise your hand right now.
Oh, I'll take comments too.
And well, I'm gonna if they don't raise their hand, I'm gonna call on a bunch of people that commented in the chat if there's no questions. Any questions? Up. Wendy Elford has her hand up. Hi, Wendy.
Hi. We were having a great time. First of all, thank you very much, Alicia. That was wonderful. I've been a fan of Tensegrity as a physiotherapist for a very long time. Something I read probably about 15 years ago has just stayed with me. And I read some work by Dr. Levin, who was there at the very beginning. And it took a lot of close reading, but he does a lot of the anatomy, and he shows how the senses and the blood vessels are intertwined in the fascia, which are part of the whole tensegrity system in the human anatomy. Okay, and I've done both neurology and orthopedics. So I've seen, and neuroscience and such. So there's, I think, a really interesting link between what you've said here and constraints, because if the physical environment constrains someone's posture and therefore how the compressors and the tensors are acting together and the postural sets that they sit into, we all know that memory is coded. If you look at Feldman Barrett's work around emotion, how emotion is made, it's made in the instance of the posture and the chemical soup that's flowing in someone at the time and what they see visually, and it makes a set. And that, if you've got groups of people who are in, say, a constrained space, and I do a lot of environmental design, I'm fascinated with the idea that what you've just shared shows a link between culture and the physical environments that people are in directly through this idea of game, this idea of tensegrity, mainly because the anatomical structures are sending the signals of the posture to the brain across the whole body because of the operational shape.
Correct.
So I'm wondering if you could riff a little bit on that, because I'm excited that then takes us down a wonderful path of culture more directly from space, like spatial configurations and constraints.
What I wanted to do in Context Changes Everything is take a look at how parts and wholes interact. And of course, you have the whole of the organism, you have the whole of the physical environment in which you are living. You have the culture in which that living environment is manifest. And so what you have is levels and layers of constraint, all operating as if you had multi-dimensional tensegrity structures, and each one of those red links is a different kind of constraint. One might be a hormonal set of constraints. One might be immunological. One might be neurological. One might be, and then overall you have the homeostasis constraints that hold all of those more local one together. And then the homeostasis might be disrupted, as I tend to think things like PTSD is a disruption of the homeostatic settings. So it's all of a sudden screaming all the time instead of going back to baseline normalcy. So you have all of that. You wonder whether cultural disruptions are the same kind of problem, that they are not able to maintain the organization, and Chris Matz's favorite term is not fit for purpose, fit the purpose, right? So then you get a mismatch, a discount, and out of kilter. See, what's interesting, I love that notion of out of kilter, because it's not like any of the parts are broken, which is the way we think of things breaking, is that the actual part breaks. Well, that's true if you have a fractured femur, a fractured radius. But out of kilter means they're not integrated, linked together the right way. And I think that's what goes across culture to physical to organism to suborganismic phenomena.
Yeah, I'm thinking one thing locally in a single person's body gets ricocheted through a meta system, not only their own system, but because of the chemical and neurological makeup and the fact that I can touch myself here and it's felt up here.
Correct.
And not just it's not just the neurological conduction, it's actually the pressure is actually very subtly echoed all the way through my body. And the chemical soup that's coming at me from other people, like pheromones and things like that, are coming into me and also acting locally in the physical structure. But that, and every person and every condition that every person is collectively experiencing, that's a pretty neat
really,
way of tying it all together.
It's really amazing. And the interface between each of those.
Yeah. Yeah. The very much more direct explanation, I think, for how things propel quickly between systems, because the sensitivity of one person's system, who's a good sensor for a particular thing, can then ricochet to other people who using other mechanisms, even though those other people aren't sensitive to it.
Yeah. Thank you. Yeah, that's absolutely. I'm hoping that this applies to the abiotic as well as the biotic, and in the, you know.
Okay, any other questions? Wendy, or were you done, Wendy? Yeah,
Wonderful.
okay. Any other questions? What's interesting, Alicia, is that, you know, this fascia discussion, because you can damage the fascia and then it's replaced and then the information flow changes dramatically.
Correct. I had a physician tell me the other day that people don't realize when they have very calloused feet that they tend to fall more, because the signal of the ground gets distorted because of the callus on the bottom of your feet. And so the brain doesn't know what's going on in the ground because that interface is not working the way it should. And that's the notion of how those constraint settings are determined is really interesting.
Yeah, signal interruption. And but it's also being able to recognize that the signal has been interrupted and that now the information flow is different.
Correct.
Right, because I'm sorry, go ahead.
No, I would think that if it happens slow enough, it's the frog boiling in the water, right? You don't if all of a sudden you had some rubber booty put on your foot, you'd know that you were not getting quite, kind of like when we put on gloves. I can't do anything when I've got gloves in my hand. But if it's gradual, you may not notice.
Yeah. Okay, any other questions before I start asking people in the chat what they were talking about? Anybody?
I'll go real quick.
Who was that? Oh, hi, Jabe. Yeah, I was going to call on you anyway, Jabe. So
I was going to call on him if you didn't.
All right, Jabe, you're up.
I had like a couple thoughts. One was that I was waiting for you to use Fuller's Tensegrity to kind of talk about. So he's really obsessed in Tensegrity, right, with dematerialization, in the sense that, like, what he is, one of the things he's primarily interested in is that he's identified these rigid structures that have the minimum amount of material required to make them rigid. So in a way, there's this sense, like when we looking at computational complexity, for instance, of identifying a minimum set of rules to establish a reproducible system. That's one of the things he's like doing with the system.
Yeah.
So I think there's something interesting there around, again, like you're getting it through your infodynamics and other stuff around this idea of like efficient structures, that the Tensegrity is allowing for a specific kind of efficient structure. So that's one of the things that I was interested in, that I was wondering if you would play with at all. I mean, he had this idea, right, that the other thing, he had this idea of a floating city, right? So that one of the reasons he's interested in dematerializing spheres in particular was because he basically wanted to make hot air balloons out of them, where the idea was he needed to be able to build a big enough structure so the internal amount of air was large enough that it could be heated by the sun through a barrier, and that then these tensegrity structures would start to float up in the air by themselves, right? So he's really interested again in these efficiencies in order to create these kind of interesting dynamics. But the other thing that I was thinking about a little bit when you were talking in Infodynamics part about the tensegrity stuff too is like, I don't know if you've ever played with making a tensegrity structure, but
Yeah.
there's like a pop-in moment, right? So like you get all the pieces in, but the final straw or structure you put in there, you have to pull it into shape, because that's the moment when the structure takes shape because the tension is occurring. If that makes any sense? It's like a pop that happens. And in my dissertation, I talk a little bit about this idea where like evolution is about like pushing things up these little hills until they hit divots, like the pop of the structure coming into place, so that they stabilize a little bit. So in a way, like creating these efficient structures requires an input of energy in order to create those stabilities that allow you to kind of build the larger complexities on top of them. So they're always like a moment, a burst of energy that causes the stability to occur that then can be, used in other parts of the system. So I was thinking about those curves that you have and things like that, or the temporary stable points, as being moments when those things kind of like click together and stabilize a little bit against the environment, so that there's like an investment. So there's like, I guess I'm trying to say like adaptation requires something other than efficiency, but the resulting structure itself is highly efficient. So I think there's a weird paradox there. Anyway,
I would think that in the case of constraint, it's a closure of constraints, right? That pop would be given by the closure of constraints. It's not a literal pop, but it is what affects the phase transition, the phase transformation.
Yep.
Since I want to emphasize context-dependent constraints, I prefer to use the word effective rather than efficient.
Yep.
Because that tells me that if it's an open system and it is constantly getting input from the environment, it has the hope of being responsive to the environment and therefore more likely to be fit to purpose than if it's just an abstract notion. That's why I like the notion of constraint, because I think I can ground it in all the dimensions, in culture, in the physical environment, in history, which is the temporality that you don't get that much of. Prigogine used to say thermodynamic structures are temporal, but they're not historical. Because for Prigogine, a historical structure like the snowflake, the actual shape of the structure embodies the trajectory it went through. And I would say, back to Wendy's point, that is probably true of posture. That is probably true of all historical and cultural characteristics. We like to think we can start from scratch. Ain't no starting from scratch with biohuman. It's almost impossible.
Yeah. I guess that'd be the last little thing that I have some objections to people like Fuller in general, and I think that you're hitting towards the parts, right? So he's trying to identify a set of like universal structures, these tensegrity structures, and stuff like that are acontextual, exist
correct. And as you say, dematerialized. Right.
And dematerialized.
Right. But maybe that's why I had read it him years ago, and then I hadn't gone back to it. But when you think of, well, perhaps, and I tried to download some little videos from YouTube of these, and they wouldn't let me without all sorts of hassles. But in a sense, constraints are like the invisible
100%.
Right? Connectors, the tensile elements when you think about them in terms of constraints, not literal pushes or pulls or physical phenomena, no matter how flexible the rubber band is, there you're still transferring energy. I don't know where you look at, but when you talk about feedback or autocatalytic present, that closure of constraint, you're talking about a change of probability space, a change of, and that's a much harder kind of tensile element to wrap your head around. It gets a lot, and then if you add time to boot, it just becomes extremely difficult.
I think it's really interesting, Jabe, that what you brought up in the chat as well about the adaptive capacity and evolvability versus maintenance or stasis.
I love that. I love
that is because that, I think, when you start to apply this to organizations and things, I think you really see that. I mean, you've actually called for a different term within adaptive capacity for those two states.
Correct.
So thanks.
That's why Dan Brooks, and I've used it a lot. He and Sal Agosta. I didn't have that reference, but look for sloppy fitness. And the authors are Agosta, Agosta, Salvatore Agosta, and Daniel Brooks. And their argument is that this misinterpretation of survival of the fittest is nonsense for a whole bunch of reasons.
Yep.
It's not fittest in the sense of a race where one wins and then the others get wiped out. It's more the term fit, and I use this over and over again. The notion of fit in biology is more like fittingness. It's more like when I go to a tailor to be fit for a suit. It's a mutual adjustment kind of thing. That's one thing. But in addition to that, it is sloppy. It is not a one-to-one. My phenotype is exactly matched to my environment. No, that's why I emphasize multiple realizability. I think the fittingness is multiply realizable. It could be this, but you know what? It has the capacity to be this, but a little bit different over here. Now, obviously, the question would be in each particular case, how far does that misfit? Think of a bird. Nobody thinks of a penguin. You think of something that kind of looks like a cardinal or kind of looks like a robin, because we think of an exemplars, and exemplars are much more generic. Well, yeah, that's sort of very typical, but one might be blue and the other one might. It doesn't matter. So when we translate that into social organization, how much of a misfit can something be from the image that I had, that you're within the adaptive capacity? Yeah, you're maybe not quite the norm, but you're still within viability, I guess you would say. That gap between H max and H actual would be viability. Or are you completely off the charts and then you're in the realm of dysfunctionality and abnormality, and really not abnormal in the sense that you're not quite at the peak of the Gaussian curve, but you're completely outside of that possibility space.
Yeah, and I think one of the things, you look at Schoen's, or you look at Ostrom's, people who have design principles around complex systems. Yeah. Both of them have a principle around minimizing specification, which again we could relate back to this idea of tensegrity, or dematerialization, which is what you're actually looking for in a well-designed system is the minimum specification to allow it to reproduce itself over and over again, right? What you don't want is over specification, over constraint, over binding to any particular
That's senescence. You're over connected. Correct. That's over connectedness. You're too perfectly aligned to the current conditions, which means as soon as that current condition changes, you're in trouble because you have no adaptive capacity.
That's right. Well, you're over. I mean, so like the capitalist system theory is roughly that we're over constraining bunches of systems, right? And in the
Right.
long term, the efficiencies that we're currently extracting value from are the things that will kill us off in the long run. So I mean, these are all you see these types of behaviors over and over
Right.
again. Okay, I'll stop. But thank you so much. It was so
Yes. Okay, Trent has patiently had his hand up. So Trent Hone, I'm going to call on you now.
Okay,
Hey,
great. Thank
Trent.
you. Really enjoyed the presentation, and I like Jabe. I'm grateful for you for that click in idea, because that gives me a nice introduction. I feel like there's a click in piece for this whole thing that is missing for me, which is wrapping up Tainter's concepts from his book. He's looking for a grand unified theory about societal collapse. So for a lot of the book, he ignores context. Obviously, we respect context and think it's extremely important. But he thinks, look, eventually you get to a level of complexity where the adaptability is not there, and then you get a contextually specific moment that precipitates some kind of collapse. Now, that moment, that trigger is going to be different depending on what society you're in. But his argument is that this is just a symptom. This is a sort of a natural factor as societies get complex, and that doesn't seem to fit well with the slides that you were presenting about Salthe's idea. There's the one that has those two lovely lines about sort of the max and then the actual, and the space in there is your adaptive capacity, and it goes up. Tainter seems to think that eventually goes down.
Correct.
And one of the things I'm very curious about is what are the triggers that cause that to go down? Because you're arguing for a certain approach that is going to maintain that gap, that's going to maintain that evolvability.
Yeah.
Well, how does that in a human society get less evolvable? I suspect one of the things that I think would be interesting is to think about it in terms of high gain and low gain,
Yes.
right? As you
Yes,
organize
yes.
to get more low gain opportunities, does that bring along a path dependency that locks you in, sort of a constraint regime to certain patterns of adaptability? So you are adaptable for certain kinds of stimuli, but less adaptable for others. That's where it seems to be starting to make sense in my head, but I'm curious to know what you think.
That's a tough one. Trent and Chris Matz and Mark Bergauer and I battle out these questions on phone calls, and we never, it's just really interesting, because the question is, sooner or later, does adaptive capacity run out? Socially, societally, we study 1848 as a transformative period in Europe, or 1968. Well, it was transformative, but it did not collapse. So how much transformation can there be? What can you do with an old suit that you can change it and take it to the fantastic tailor that will rearrange the components, and it looks a little bit different because you don't have the money to go out and buy a new dress? So you go to the seamstress and she fixes it all up, and it looks like you've got a new dress for the next dance. But at what point does that become impossible? Is it the conditions in the environment? Tainter makes a big deal about lack of fuel. Ultimately, it is you don't have enough fuel available, even on a low gain, or you don't have enough fuel to maintain the organization that would be able to tap into the low fuel, so it becomes a vicious cycle that simply runs out. Or are there, to use my terminology, are there forms of constraint that can override the existing kind of fuel and the existing constraints? So that's why I'm interested in AI, or say nuclear fusion, because Tainter has a couple of very nice YouTube available podcasts where he even addresses the notion of nuclear fission. He ends up saying, yeah, but what does it cost to refine the uranium isotope, right? So no matter how much nuclear power you're getting, it still is costing an incredible amount of money to refine that nuclear isotope. And then you've got the problem of waste that you have to deal with, which costs you a lot more money to deal with the problem with. So my question is, does nuclear fusion not just add another one of those humps from the food gathering ants to the grasshopper feces to the leaves to but rather that it actually changes the possibility space altogether with a entirely new type of fuel? And as I don't know nuclear fission, I don't know any of this stuff, but I looked at how much does it cost to build a nuclear fusion? And the idea is, well, it would cost a lot more to have a nuclear fusion processing thing now, but once you get it going, the elements that it uses are a lot less. They're a lot more available, like lithium and deuterium and so on, a lot more available than mining uranium. So the question is, can we come up with new types of constraints? See, I do think that genetic information at the origin of life reset the whole possibility landscape. It wasn't just one more type of rock. Correct? One more, oh, this galaxy is spiral like this, the other one looks like that. No, this was a whole qualitatively different phenomenon, right? So what was that? A new kind of constraint, genetic information that can be preserved across generations? So you don't have that preservation across generation in thermodynamics. It's just getting deteriorating and depleting and depleting and depleting till it's gone, correct? You don't have the preservation of form, the maintenance of structure at all in classical thermodynamics. Correct? Tell me if I'm wrong. So, Trent, my answer would be, it's got to be either you can't beat Mother Nature, you can't beat the second law, sooner or later it's going to catch up with you. Or, yeah, but you can delay it a hell of a lot longer by coming up with qualitatively new fuels and qualitatively new forms of constraints.
Yeah, which like life is a reaction to, in a sense, right?
Correct.
If we take the idea that, biology exists, or the encoding that you just talked about, which is a fundamentally different dynamic, I buy into. If we accept that is a result of patterns of thermodynamics,
Absolutely.
Local increases in complexity that eventually give you, if you look at the entirety of the system, a more rapid increase in entropy or decrease in entropy, then
but with increase in form.
Right.
Correct.
Correct.
Correct. Which is what, when Darwin wrote in 1848, and the heyday of Clausius and the whole thermodynamics, nobody can understand, well, but they're complete odds. What Darwin is saying is increased complexification in biology, whereas thermodynamics is saying total decrease in organization and order, because there is no storage of energy in the form of structure or of information, which is why the whole idea that if a black hole eats up all the stuff around it, where does the information go? Correct? So the relationship between matter, physical thermodynamics, and information is such a mess. It has not been resolved, and you get different definitions of information to try to explain it. But if information is organization, well, one would expect that in the black hole, that organization disappears, correct? I don't know. Asking
Thank you.
this is chutzpah on my part because I'm not trained in this.
That's what we have the lounge for.
I guess so.
To float these kind of ideas out there and see what happens. Trent, I was specifically thinking while you were talking about the assumptions we make as well within these systems, right? Because I was thinking of the global supply chain, and that assumes a certain natural stasis in terms, or, a stasis within nature that may not exist. So, for example, we assume that currents will stay the same, that, we will be, that the climate will remain the same and allow us to, dock ships in the same places over and over again, land planes in the same places over and over again. And we are seeing challenges to those assumptions.
Correct.
That we may or may not be willing to adapt to.
Correct. Or be able to.
Right.
Yeah, that I think is a lovely example of how quest for efficiency has driven out, because we all remember the Evergreen ship that got stuck in the Suez Canal. Yeah, it's a great example of adaptive capacity being efficiencyed out of the system.
Correct.
Yeah, that's exactly what I was thinking about.
Yeah.
Okay, I see a hand up. Yuliya, you have your hand up. Thank you, Trent. That was really, really interesting. A great exchange.
Thank you, Trent.
Yuliya.
Yeah.
Yuliya.
Was so impressive, Alicia. Thank you so much. I didn't know. I have a bunch of different ways where my mind goes whenever I'm thinking about every next slide you're showing, because it seems to me that you, in the, the smartest way in the world, described how such a thing as climate crisis arises, right? Because when we're talking about low-hanging fruit and extracting the fuel just from under the core, and that's been done by 5 countries maybe, and just burning it in, and then we're reaching for the first time 1.5 increase in degrees. And now we have the whole new set of constraints with all those fires, tornadoes, and so on. But what you are saying is it's not only the collapse of the energy consumption. What you are saying, it is the societal collapse.
Correct. It's the complexity that collapses.
Exactly. And so what you are saying is that all this circus that is happening with all the politicians, with the propaganda, with the social not believing in COVID jabs, or not believing in the democracy, or not believing in all these things, just like overall madness. You just explain why we're living in this overall madness, just because we have been using so much energy that we are collapsing as the civilization. So, for example, I was thinking about Rome collapsing, and what you were saying about taking the energy from everywhere and becoming such a coloss on the legs that are too rigid to sustain this huge empire.
Correct.
And then I immediately jump into why USSR collapsed suddenly, that nobody expected it to collapse in the way, like in August, there were the speeches that it's never going to happen, the so-called Kiev speech, and 24th of August 1991, it collapsed immediately because there were a lot of signs of not being able to take the information, as you said, the information dynamics, not being able to take all the energy, not being able to sustain all this expansion, and the constraints changed. Correct. So the idea is that the empire collapsed within days. You just explain why USSR collapsed.
There's a YouTube video with Tainter, and I can't remember who the host was. He's French, but I can't remember. And he's an expert Roman historian. He's a historian of Rome, and he goes through what happened in the first, and it's very interesting. But again, the question is, in biology and ecology, how does nature handle this? And Salthe's point seems to be that they are able to maintain a level of complexity that is below maximum complexity, such that they continue to allow adaptive capacity to, there's enough slippage, or there's enough sloppy space there that you can tap into it in a real emergency. If you're using up all adaptive capacity under fairly normal conditions just to grow, then that is a recipe for disaster. It's interesting because one of these days I'm going to have to sit down. Every time I come across one of these examples in biology, I'm going to have to write it down. But I don't know how many species who limit their reproduction in times of scarcity.
Mm-hmm.
So the animal is able to understand that they, it's one thing to maybe make some inroads into under emergency situations, but if you do this all the time, if you continue to grow at an exponential rate, sooner or later it's going to collapse. And they manage to maintain a steady state. Obviously, the predator-prey cycle is a beautiful example of that maintains itself, because as soon as the predator eats too much prey, then there's not enough prey, and so the numbers of the predators drop. See, the question is that what will happen to social organization, that you have to wait until that number of predators die off until the others start,
or we kill them, yeah,
or
an
killed
emission.
off one way or the other. They collapse one way or the other. Correct. And that's what's frightening.
But what amazed me is that you showed why this kind of world level tension between autocracies and democracies have a chance. Because in democratic environments, there is this kind of resilience and what you said, varied
behavioral variability.
Exactly.
Yeah.
Variability and varied action and non-central behavior. And while autocracies are this colossus, or if you wish, this David and Goliath, right? Mm-hmm. When you have this huge, big, not being able to turn, but extremely pumped up with money and with the power and with the all this kind of arms, will be able to collapse when it gets hit into the hill, just because of the connected action, varied action.
Yeah, I was thinking of the behavioral role of influencers did not exist 10 years ago, right? That was not a behavioral role, correct? And how many jobs and roles exist today that did not exist before? I wonder, I would love to ask Salthe, if I would have been able to ask him, do you consider this an example of resilience? You wonder if that was some of what he had in mind, but people who no longer found jobs in regular manufacturing or corporate settings, but rather use this new enabling constraint of the internet and social media to create an entirely new genre of lifestyle and behavioral pattern. Kind of like when the termites run out of resources, or the slime mold, and they don't just aggregate, they organize into a multicellular organism with a head and a tail and so on, that they had the adaptive capacity to transform their behavior, their actual biological structure. And then once conditions resume normalcy, then they go back to becoming independent unicellular organisms. What is the social equivalent of that?
I can tell you.
Yeah, I can imagine.
I can definitely tell you. That's the army, which is contained by all the people who are society, and they group together to fight against this Goliath, and they have this connection one with another, and they are waiting till it is defeated so that they can come back to their normal lives. Because, for example, my friend is the the dean of the university, and he wants to come back and to teach again, but now he's got a more urgent thing to do.
Yeah, it's interesting. That is the social version. Yeah.
Okay.
Thank you very much. You're
Thank you,
amazing.
Yuliya. That was really great.
Yeah.
I don't see any other hands up, but the chat has completely blown up. So,
Oh my goodness.
I'm exhausted from the chat. But I will say, Anna, you had, I don't know whether it was a question, I don't know whether it was a sort of rhetorical question, or did you actually have a question for Alicia?
It was less of a question, more of an area for exploration, but we are at time. And I was just curious because I've just been exposed to the idea of tensegrity. So I was interested in hearing more about the relationship between structures that display the tensegrity and redundancy, being inspired by Jabe's comments.
Yeah.
But I don't know if we have time for that.
We can go as long as Alicia would like to go. So, Alicia, if you want to take it on, go for it.
I'm not sure I have an answer to that, because as Jabe was mentioning, it's almost like tensegrity tries the minimum number of material elements to maintain the structure, as opposed to, you onboard replacement parts and redundancy. But after a while, you can have so many redundant parts, but you can't. When I flew to Havana, and this is still, even to this day, since there are no diplomatic relations with the United States and there's the embargo and all the rest of it, the American Airlines plane flew on board a spare tire, I was being told by the people who run it, the redundancy that they expect, well, a tire is something that might likely blow, but they can't onboard an extra engine. They might have cowlings available at the Miami airport, but they don't have an extra engine. So it gets to the point where, is tensegrity an attempt to bypass the problem of having redundant structures? It really is very expensive energetically to try to see, and this is obviously down Jabe's alley, and that is that the design of the structure would take care of its resilient and its preservation of its integrity. That, I think that's the $64,000 question, whether the design conditions, especially the design of the different kinds of constraints, would be able to manage that in a way that just adding extra parts gets awfully expensive.
I was wondering about that in relation to, the differences between tensile parts and constraints, whether it also partially has to do with how you negotiate that need.
Exactly. And I think that Fuller was primarily concerned with physical objects, whereas I'm more interested in constraints generally as those influences that change the probability and likelihood of this might happen rather than that, or keep these interlocking, interdependent dynamics that keep cultures together, that keep what we call families as families and that sort, or, you know, societies together. How does that work? And clearly, for all of these hierarchy theorists, it takes a number of layers of organization. You know, one or two alone probably won't do it. The system won't stay whole with only a leader and everybody else is a follower. Rather, you need a number of different levels of organization, each with distributed control to each other and yet interrelated among each other to get that kind of tensegrity constraint dynamic that has that capacity to bend, to be flexible, to adapt, to evolve, all of that. And that would be, if we started thinking in this way, that's the kind of research we would be engaged in, correct? It would seem to me. How can we keep this system going without freezing it, without entrenching existing propensities, without becoming senescent so that a serious change in conditions and culture won't destroy it? Or render it unidentifiable, because I think that's the problem. It loses its integrity, it means it loses its identity. It is no longer able to continue by adding on new information, but rather the old information just this. I love that word, integrity, because it has the integrity, it has the normativity, which is, if I had done what I had said I was going to do, I would start bringing in normativity and values exactly at that point. The normativity and value rests on those interlocking dependencies that produce emergent value, emergent function.
All right, well, you're going to have to come back and talk about that.
So.
But Jabe, I just want to say, Jabe, she used your name. So do you have anything to add to this?
Oh,
So
is that the rule?
The one thing I was thinking about when I was listening to this last kind of bit of talk is just, so when we think about resilience, one of the terms that we use in safety 2 theory is the idea of drift. And so I'm thinking a little bit about this paradox as well, which is, so we have this paradox where we don't want the system to be too rigid. Because if it's too rigid, it becomes brittle. So we want it to be adaptive, which means we kind of want it to be able to wiggle and do novel things and things like this. But drift is, in fact, a social problem in which we allow the system to wiggle in ways that the combined wiggling causes the system to collapse in and of itself. So there's like this meta system that has to occur, like this other set of constraints that has to occur on top of the system, like we're getting another hierarchical level of design here, where we have to help the system observe what good and bad wiggling is. And this might be roughly the idea in tensegrity that it's mutable but not any shapeable, right? You can't make it anything.
It's not infinitely change.
That's right. And so there's something in there that I think is, because when I was listening to Alicia, I was kind of like tallying up. There was a lot of points towards it can't be too stable, but I'm trying to find the other side of that.
Then it's old-fashioned chaos. Correct.
Yeah. So, and the drift, I think, is just an interesting case of, again, we're trying to design a system which intentionally is adaptive. It intentionally has ambiguities in it that intentionally allows for certain behaviors that are unexpected. But then how do we also design the system to go, okay, so and partially it comes from the plane conversation that Alicia was talking about. A lot of this safety 2 theory comes from people flying planes and not bringing along the redundant parts, because the plane flies without the redundant parts all the time, right? So do you need it every time? Oh, well, it just happens if you don't have 2 of the redundant parts, then the system can completely collapse. But how often does the 2 parts interact? Not very much. And so the drift occurs. It becomes socially acceptable to fly the plane without the extra bolts. All of a sudden, the plane will start flying out of the sky. Right, so this drift problem is maybe the other side of over constrained. Then there's it's not under constrained, it's drifted in a way. Anyway, that's what I was thinking about.
Okay. Anybody else? Does anyone have anything to add to that? Any more questions? Comments? I'm looking at some of you. You've been very active in the chat. You know you want to. No? Okay. Well, oh, Wendy is raising an actual hand, not even a virtual hand.
Only because the whole conversation around boundaries and boundary triage and such, Midgley's work,
Yeah.
it just keeps on popping up, and I just think that I'd be really interested in Alicia's thoughts on how boundaries and setting boundaries fits in with what you've just presented, because a lot of people get blown up by very big systems and the connectedness. Then they have to put some form of boundary. So, I mean, it is a constraint. Maybe it's as simple as that.
Well, as I understand it, the prokaryotes, the early form of life, had had the cellular equivalent of rigid exoskeletons. And so when you see a horseshoe crab or you see a lobster, that's an earlier form of life than the eukaryotes. I'm missing my phylogenetics here, but I think what I'm trying to say is correct. The prokaryotes had rigid exoskeletons, whereas the eukaryotes had porous, permeable membranes. But I guess the person who's coming into the White House never heard of that transition because they keep talking about walls. Whereas it seems to me walls transitioned into moats, which transitioned into letters of credit, which transitioned into visas, which transitioned, in other words, they are more permeable, they are more nuanced, they are more like interfaces, passports, visas, and so on, rather than a wall, correct? And it seems to me that the concept of boundary has evolved to support that more sophisticated phylogenetic level. Where are the boundaries of an ecosystem? Try drawing those boundaries. Well, they tend to be drawn in terms of energetic phase differences, right? What Barbara said earlier about, well, we don't know these conditions that we assume that all the tides are going to stay the same way and so on. It's the scale is so much larger that the phases of that level of organization, the boundary between that and where we live is very difficult for us to understand and perceive. So I would say the notion of boundary itself has changed to Paul Cillier, who was a wonderful complexity scholar and he died too early, he used to talk about in complex systems, boundaries are active sites, sites, like the eardrum. The eardrum is not a wall. The eardrum is not just a passive sieve. The eardrum is an active site that negotiates the dynamics inside with the energetic waves on the outside. And so that's what we have to think of boundaries in social systems more as, I think.
Okay. Anything else? Does anyone, boy, that was awesome. Anything else? Does anyone have anything they want to add to that or any other questions they want to ask? You don't get this opportunity all the time to ask Alicia questions. So, okay. I don't see any hands. So Tiani?
Oh, Tiani, good.
I'm taking the baton to close us out and wrap us up.
Okay.
Yeah. So yeah, I just want to thank you so much, Alicia. Such a great discussion and deep ideas, deep and meaty concepts. That it's really awesome, and we really appreciate your insights and always being a guest on the lounge. And also for all the attendees, the questions, the additions,
thank you all.
whether in the chat and out loud, I think that helps with our making it more vibrant and more interesting and
Thank
fun.
you all. Thank you for listening.
Yeah.
And I'll take all sorts of comments and feedback. Just send them in, folks. Please. I mean, I've been winging this, so let me know. Thank you.
Yeah. Yes. So thank you so much. And before we wrap, just to announce, we're excited to announce we have Barry O'Reilly will be joining as a speaker on February 4th. And then we have Dave Knoll on February 18th. So we hope to see all of you there for more insightful discussions. Thank you so much and have a great afternoon or
Thank
evening
you,
or wherever you
folks.
are.
Thank you. Bye-bye.
Bye.
Thank you.